All right. Hello, everybody. Welcome to CS291A Differential Privacy. This is our third lecture. We're going to continue our journey on learning more mechanisms that gives you differential privacy, more mechanisms that satisfy differential privacy, and with one application in mind, and of outputting as many bit of information as possible by answering like as many linear queries as we like, and try to answer them the most accurate possible. Okay, so in the last lecture, we've formally defined differential privacy. So we defined epsilon delta differential privacy, where epsilon and delta are called privacy losses, and we made a number of interpretations about this privacy definition and justified why it makes sense and why it satisfies all the nice properties that's needed to handle the real life challenges of possible privacy breaches and data linkage attacks and so on. And we've set up the notations. How do we represent the data set, and how do we measure the distance between two data sets through the L1 distance in the histogram representation of a data set? I received some questions after the lecture last time, so I'm going to go over the representation of the data set again in today's lecture to make sure everybody's on the same page. Yeah, so my philosophy of teaching is that everything that's worthwhile teaching, like all the good materials should be taught at least twice. So starting this lecture, I'll try like giving a quick recap about what happened in the last lecture without necessarily going into all the technical details, but I'll try to have a recap about the materials that we've learned from the last lecture. Okay, and in the second half of the last lecture, we learned two mechanisms and proved that they satisfy differential privacy. So these are the Laplace mechanism and the randomized response. And you got a flavor of what a differential privacy analysis looks like. Basically, you wanted to check your privacy definition by showing that for any pair of neighboring data set and for any possible output space, you can prove that inequality. So it goes in the more or less straightforward way of starting from the left and trying to fill in the middle and arriving at the right hand side of the inequality towards the end. Okay, so we'll go over like a few items from the last lecture. So the first is one that causes a bit of confusion in the last time. So there are several different ways of representing a data set, and they're overloaded notation for X and this calligraphic X that costs the notation. So let me try rectifying these issues today. So there are three representations that we talked about the data set in the last lecture. So I'll start with the last, called standard data table representation. So this is the most typical representation of the data set. So consider a data table that's n by d. Okay, n by d, and d is the dimensionality of individual data points, and every row of this is one person, one data point. Okay, so then I guess this is a standard like data table kind of representation, and you can represent this by an n by d matrix. But the thing is that in differential privacy, often we wanted to cover the space of all possible data set with an unspecified data size, because the data size is also private information. So we want to make sure that as we add or remove individual data points, then the n actually changes from either n to n-1 or n+1. Therefore, when we consider the space of all data, we want to consider, let's say that each data point lives in the data space X, and a generic data set in a standard data table representation belongs to the union of empty set and the union of n from 1 to positive infinity, all integers, and x to the power of n. right? So they live in the product space of an n tuple of individual elements. So this is a standard representation, and we call this X star, right? With a star on the superscript representing the unspecified size of the data. Okay, now let's try converting this into the histogram representation, which is like which is what we talked about earlier, and how it can be used to measure the distance between two neighboring data set in terms of the added distance, in terms of adding or removing individual data points. Okay, so in a histogram representation, a data set X is in the space of, this is the space of all natural number to the power of the cardinality of the data space. Okay, so I'll give an so I gave an example last time about the apple, orange, and pear, right? So basically this enumerates the histogram of the number of items that are apples, the number of items that are pear, and the number of items that are oranges. So if X is so we can also give a more realistic example of, say, this is the space of the data set is D Boolean variables indicating whether your salary is larger than 50K, whether your age is larger than the voting age, and whether you have any children, and so on. So these are three attributes. So the cardinality of this data space is then 2 to the power of D. So this histogram representation of the data essentially enumerate all possibility in this 2 to the power of D elements, and then count the number of data points that's contained in that little bin of this histogram. Okay, so I think in the database literature, this is called a multi-set representation. Yeah, so this representation is more or less equivalent to the standard data table representation with unspecified size, except that the standard data table sometimes, like, the ordering matters in which data point appear first and which data point appear second. But in the histogram representation, everything's equivalent, and there's no notion of ordering. So it supports all the algorithms that's so-called permutationally invariant to the data set. If you shuffle the data set and then apply that algorithm, it gives you the same thing or same distribution. Then for those algorithms, the histogram representation and the standard data table representation, they're the same. But there are sometimes, like, a fancy algorithms, say those that are online, or those are streaming algorithms that takes one data point at a time. Then the distribution of the output of those algorithms will depend on the ordering of those data points being seen by the algorithm. So those are the cases when there is a distinction between these two representations of the data. Okay, so I hope that clarifies things a little bit more. I guess more that we can also write I guess hist of the data. So X is sometimes defined the hist of the data. And then xi's coordinate is the sum of I from 1 to n indicator of whether this phi I is equal to the ith element in the data space, and then basically you sum it up, right? And alternatively, the data table representation would be phi I, phi 1, phi 2 to phi n in, yeah, I guess let me add transpose in, I guess R to the n by d, right? So that's the data table representation. I can convert it into the histogram representation by summing the indicators. All right, so finally, this indicator representation is it's just something that we were dealing with. Yes, it's something that before we get there, so one nice thing about the histogram representation is that we can actually measure the distance between two data sets. So let's say we have x and y, and x minus y. One norm is equals to number of data points we need to add or remove to go from x to y, or vice versa, right? So this is a convenient representation that allows us to say that the one norm of the two data set being smaller in its histogram representation being smaller than one, it says that these two data sets are neighbors, right? And it helps us to define like the neighboring relationship in terms of add or remove. However, on the other hand, the data table representation is more convenient when we are dealing with the replace neighboring relationship, when we add or when we swap out one individual, for instance, the nth individual from the data set, and then replace it with someone arbitrarily different from the data space. Okay, so lastly, the indicator representation is basically an indicator of inclusion of say a given population of individuals. The bit vector selects a subset of the individuals who is part of the data set, and then it comes with some unspecified associated features that are typically unspecified. So this in this representation, when you talk about queries, so they sometimes depend on those associated features. So we will not be dealing with this indicator representation that much. So let's focus on the standard data table representation and the histogram or multi-set representation of the data set. All right, we gave a somewhat lengthy recap of the data representation of the data set. Now, for the definition of differential privacy, so this is it. I hope you managed to take a closer look at the definition mathematically. It says that for any two neighboring data set and for any possible output, the probability of observing this output is bounded in a multiplicative way and in an additive way in a parallel world where a data set is a little bit different, and then you receive the same output. Okay, so this shows that like for any two neighboring neighboring data set, the output the distribution of the output are more or less the same. Therefore, it is private. And when delta is 0, we say that M is epsilon pure differentially private. And what are the measurable set here? So it is an arbitrary, say, interval and the collection of all the intervals, and the probability is just area under the curve for those intervals. And what's this definition? Like when delta is larger than 0, is saying that we are ignoring those measurable sets that doesn't happen with sufficiently large probability. But for all those that happen with large probability, it is a multiplicative part of this bound that kicks in, which says that we want the ratio of the two area under the curve to be bounded within each other by e to the power of epsilon. And when epsilon is small, this says that the two distributions are more or less the same, even if the events are very rare. So in this sense, it's a very strong notion of privacy. We talked about randomized response, which we introduced in the first lecture. The randomized response is very simple. Basically, the data set is just a bit of information, and you toss a bias coin with the probability larger than 0.5 and decide to answer honestly when that happens, and decide to flip your answer when you get a tail in your bias coin. So we've shown that this algorithm satisfies epsilon differential privacy when we choose P to be equal to this parameter that depends on a privacy budget epsilon. check that this is larger than 0.5 when epsilon is larger than 0. And then we talk about how do we make use of this to create an unbiased estimator of the data of the secret bit, right? So this is a part where I also receive a question to say that can I go over this again? So here we go. So this is how we construct the unbiased estimator. And to show that this is unbiased, we simply take expectation on both sides. And since y is coming from the randomized response, we take expectation on both sides. And by the linearity of this expectation and the fact that only y is a random variable on the right-hand side, then we get this. And I guess condition on the case when x is equal to 1, yeah, let's say x is equal to 1. Condition on the true world when x is equal to 1, the probability, the expected value of y is just p, right? So we get 0.5 plus p minus 0.5 over 2p minus 1. This gives us 0.5 plus 0.5 equal to 1, right? On the other hand, when x is equal to 0, when x is equal to 0, then the probability distribution of y is 1 minus p. Yeah, by the randomized response. So we get 1 minus p minus 0.5 over 2p minus 1. And this is 0.5 minus 0.5, which gives us 0. Right. So by doing this, we've converted randomized response by debiasing and rescaling it so that this x hat is an unbiased estimator of x. We'll see how we can make use of this to use randomized response to answer linear queries like later today. Then we introduce Laplace mechanism. So Laplace mechanism like takes a query f, which takes the data set and output a numerical value in R to the K. We define the L1 sensitivity of the query, which is say that this is the largest number of the L1 distance between f of x and f of y when x and y are neighboring data sets. Right, so you max over all neighboring pair of data set, and this is the largest possible perturbation of changing from one data set into its neighbor in terms of output of this query. And when we have the L1 sensitivity, then the Laplace mechanism simply add noise to release an approximate value of this query of f of x by adding the Laplace noise to every coordinates with its scale parameter equal to the sensitivity over the desired epsilon parameter. Okay, notice that you're adding an independent noise to every coordinate of this query. Yeah, so the energy of this noise vector that you add actually scales with square root of k. Yeah, of the dimensionality. Okay, so that was a recap of the last lecture. So today we're going to finish the utility analysis of the Laplace mechanism, introducing a few and then introducing a few hammers. Say we've already been using it actually, Hofstein's inequality. If you're not familiar with it, today we'll go over that, and then we'll like try applying Laplace mechanism and the randomized response to the problem of the simple linear query release that we've seen from the first lecture, and then we're going to generalize the linear query release problem a little bit, and then try to have a sense of where we are in terms of the sample complexity, in terms of whether we're comparing the performance of the different algorithm. And then we'll see that there are actually a lot of room of improvement. And then the key item of today's lecture is about so-called sparse vector technique, which is another one of the most fundamental building blocks of differential privacy algorithm design. Once we introduce sparse vector technique and analyze its privacy and utility, if we still have time, like we'll we'll learn how to make use of SVT to obtain stronger bounds for releasing an exponentially larger number of linear queries comparing to the naive Laplace mechanism and randomized response. Okay, so that's a plan for today's lecture. Like here are some related readings. So these supplementary readings are really not compulsory, but if you're interested in understanding a little bit more in-depth information, like they are good materials to read as well, particularly on the subject of today's lecture. All right, so we'll start with the Laplace mechanism. So again, Laplace mechanism adds Laplace noise to the query on every coordinate. And what does the Laplace noise look like? The density function of the Laplace noise looks like the following. So it's like a double-sided exponential distribution with a pointy tip at the middle. So if you look at Wikipedia and then check how the analytic expression of its density function, you'll see that the CDF have a very nice form, which basically says that the two tails, if x is the two tails satisfy that they decay exponentially as you move further away from x. So this is a left tail. So this is a left tail, and 1 minus this is a tail on the right. So in other words, if we want to bound the magnitude of a Laplace distribution, so probability of a Laplace random variable b being larger than say t times b, this is smaller than absolute value. This is smaller than e to the power of minus t. Okay, so simply by adding the two tails up, and you can derive this this inequality for all t larger than 0. And then so now consider this query that output k numbers and the Laplace mechanism that adds independent Laplace noise to every coordinate, and we wanted to figure out the L infinity norm of the difference between the desired between the desired answer, the ground truth, and what we are able to output. Okay, so this is max of all coordinates f of x I minus y of I, and y absolute value, and yi is the ith coordinate of the output of the Laplace mechanism. So what we're gonna basically do is to show that simultaneously for all k coordinates, the Laplace noise that we add is smaller than some number, right? And then we're gonna put that number here, and then add all those tails up into this failure probability delta. So we don't care about what happens in this failure probability delta. The Laplace noise can be larger than my bound, but as long as we can show that the delta is small, and this is a good bound. Okay, so basically we apply this for k times. So let's say we have Laplace z1 to the k, and z1, the probability of z1 being larger than delta f over epsilon log 1 over delta tilde is smaller than is smaller than e to the power of minus log 1 over delta tilde. So I'm basically applying this inequality by substituting t to be log 1 over delta tilde, and delta tilde is something between 0 and 1, and this is equal to delta tilde, right? And then probability of the two larger than the same quantity, log 1 over delta, smaller than also smaller than delta tilde. Enumerate this for all the way until the k, and I basically add everything up, right? So I add everything up, And then I get then I get the probability of max I z I being larger than yeah, I guess the max or yeah, basically for all of them we can show that the probability yeah, let's do it the other way. This thing is smaller than delta f over epsilon log 1 over delta tilde. So these implies that like all of them being smaller than this by the union bound. So this is called the union bound is smaller than the one is larger than 1 minus the sum of probability of individual zi being larger than delta f over log 1 over delta, and this is by our bound over here, this is smaller than 1 minus k times delta tilde is equal to we can set delta tilde to be 1 over delta over k, and this gives me 1 over delta, right? So this proves this theorem 3.8 by saying that with probability 1 minus delta fx minus y L infinity norm, which is what this is smaller than delta f over epsilon log f log k over delta. Okay, and k is in this case is the dimensionality of the output of the single Laplace mechanism. Yes.
Why do you need to do union bound when you just like can you not do like a comparison? So like right there you are taking the infinity norm. You want the maximum one.
Right.
Can you not like I just don't see why do you need to do a summation of all the probabilities and do a union bound to bound the total field probability. Like can you not say just the maximum one is like less than delta, so like
yeah, you can get a slightly tighter bound with 1 minus delta to the power of 1 minus delta tilde to the power of k, right? So that will be slightly tighter than 1 minus k times delta tilde. Yeah, but 1 minus k times delta tilde is slightly a slightly simpler expression. Okay. Yeah, I hope that answered your question. Okay. All right, so like how like the key quantity to apply Laplace mechanism in practice is to calculate the so-called L1 sensitivity. So let's work out a few examples of this L1 sensitivity to have an idea like what it looks like in practice. So let's first start with the linear queries. So the linear queries from the first lecture. From the first lecture is to say there's this Q that's the indicator vector, and the linear query is a Q transpose at, and the data space X is also in a bit vector, like 1 person per bit. So this is a linear query. So the L1 sensitivity of the L1 sensitivity of this is simply Q X minus Q and say X prime, and X and X prime are neighboring data set. And since this is just a univariate output, right? Since this is just a univariate output, the one norm or infinity norm doesn't really matter. So trivially, this is just equal to the absolute value. And well, this is smaller than Q infinity and X minus X prime. one norm, and since x and x prime, they are neighboring, this is equal to 1. Okay, so this way we calculate the L1 sensitivity for linear query is 1. So how about histogram? As an example, let's say that we in an undergraduate class, we now finish the midterm and we want to communicate the distribution of the grades to the students without jeopardizing individual students' privacy. And then we count the number of people who's in the 0 to 60% zone and 60% to 70% zone, and so on. Then we now have a vector of output. Let's say that this is a vector of 5 different outputs. So what is the sensitivity for this query? Consider that you add or remove any individual. It can only any student who enrolled in this class. I guess the output can only change in one of those bins, because one person cannot simultaneously be within the 0 to 60% zone and in 80 to 90% zone, right? So when you calculate the output, takes the difference between the output and then take L1 norm, then only one of the coordinates is different, and the maximum difference is by 1, right? So therefore, the L1 sensitivity is one for the histogram as well. So next, so this one I'm gonna wanna answer from you guys. So let's say that we want to publish some demographic statistics over the map, right? So let's count the number of people in different zip codes in Santa Barbara who say by race and gender. So first of all, what is the dimensionality of this output? It's a number of zip code in Santa Barbara multiply with the number of possible races and the number of genders. Yeah, so that's the output space, right? So what is the sensitivity? What is the L1 sensitivity here? Can someone just tell me? 1 as well, right? Why is that? Yeah, exactly. This is just another histogram, right? With a different attributes. So so next, let's consider like something slightly different. Let's consider the hospitalization data of say COVID-19. So this is the let's say that we have 5 different hospital, and then each hospital is gonna release their total number of active patients every day. Okay, so the data is in the form of so the data in the form of the hospital 1, hospital 2, hospital 5, and time equals to 1, time equals to 2, time equals to say time equals to 100, and then the length can go on and on and on and on, right? So what is the L1 sensitivity of the data in the form of such big table with every coordinates being say a number 26? So in hospital 2, at time 3, and there are 26 patients in the ICU of hospital 2. What is the L1 sensitivity of this data set? This query, right? Suppose we just want to output this the entire table as the output of the query. The length of time. Yeah, that's like, could you formalize your argument? Why is it the length of time?
One patient can only one hospital at each time.
Mm-hmm.
One patient at each time. So
Okay. Yeah, that's a good point. So when we think about this problem, like we should try to think about what is the worst possible situation that would happen. What is could there be any patient that since one patient can only be in one ICU of a single hospital, so the sensitivity cannot depend on the number of hospitals, right? So that part is good. On the other hand, there could be some person who's like having a really bad condition that stays in the ICU from day 1 all the way to day 200. Okay. Yeah. So if that's the case, if that's a possibility, then this data set will have an L1 sensitivity of the length of the time horizon. On the other hand, like suppose we make some mild assumption that any patient will only be in a hospital for ICU for less than 2 weeks. Otherwise, either the patient will recover or the patient would have deceased. Then you can further bound this by saying that any individual who stay in the hospital, and in this data set, the L1 sensitivity would be the contribution of any individual data point to the entire table. So that would be, say, 2 weeks length of time being the L1 sensitivity. And to demonstrate that how we represent the data actually matters here. So what if we just transform this data a little bit by taking the forward difference of every entry in every coordinate for each hospital? Let's say that in the first coordinate, instead of in the first coordinate, we put the initial number of patients in the ICU. In the second coordinate, we put the number of additional patients in the ICU. And in the third column, we put the number of additional patients that comes in the third day. Right? Suppose we do this kind of transformation of the data, then what is the sensitivity of releasing, what is the sensitivity of the query that releases the daily new patients that enters and exits the ICU? True. Why is that the case?
Because the transfer only happened at the beginning and
Mm-hmm. Yeah, so there was a student who answered true, because the patient can only enter the hospital and then exit the hospital. So in total, the person's contribution to the statistics will have to be bounded by 2, right? So that's an excellent question, but there's a hidden assumption of that, because it says that any individual can only like enter the hospital once. So there could be someone who got COVID and then recovered and then went back home and then later caught COVID again, right? So under the assumption that this is not a kind of disease that once you get it and then you become immune forever. So there could be another reason. There could be multiple hospital entry which violates this assumption that you have. So I wanted to say that in practice, the computations of the L1 sensitivity is complicated, and it requires domain knowledge and requires our understanding of the world so that your calculation makes sense, right? And with the right assumption and the right calculation, you may end up getting significantly more powerful and significantly more accurate differentially private release comparing to suppose you do a naive upper bound of the L1 sensitivity. All right, so here's an example demonstrating the first large-scale deployment of differential privacy. So by the U.S. Census Bureau. So this was from 2008, and the website is still on, and they are keep publishing demographics data on the map on this portal that you can find here. So I'm showing the city of Santa Barbara, including the UCSB campus and the rest of the city of Santa Barbara. I guess in the middle, this is Goleta. And you can see that all these visualizations and all these additional statistics of numbers, they are published differentially privately using Laplace mechanism. Right, so we can see that there are many like fine-grained details about individuals, and and still everybody like satisfy a very strong notion of privacy guarantee, right? So I'm putting up this slide to show that like even for things that are simple as Laplace mechanism, and you can find a good application of that, and sometimes it is a killer application. And the key idea behind why this could work is really that the L1 sensitivity of any individual in any being of the histogram that they are trying to release is 1, right? So you don't need to compose over the multiple coordinates that you privately publish your data. Yeah, I encourage you to go to this website and then try it out and see whether you get numbers that make intuitive sense. All right, so now let's try applying the Laplace mechanism to answer like not just one but many linear queries. Yeah, again, let's say that in the old definition, the linear query is a Q transpose X, where Q is 0, 1 to the n, and X is 0, 1 to the n. That's a data set. X is a data set, and Q is your query. And so I'm just gonna work through this workflow of like implementing a Laplace mechanism so that we have an idea of how it works. So we start with a fixed privacy budget. So you have a epsilon budget. So let's say that epsilon is equal to say 0.5. And then we also know the number of queries that we're supposed to answer. So let's say that the cardinality of everything in this query space is k. Let's say k is equal to 100. Okay, so what we need to do is to say that after composing for k rounds, then the total budget needs to be 0.5, right? And by the composition theorem, we know that then we need to allocate a fraction of the privacy budget to every query. Let's say that we allocate that evenly. So epsilon per query would be 0.5 divided by, yeah, I guess epsilon total budget divided by k, that will be 0.005. Okay, so once we have this, we need to decide how much noise to add. And by the Laplace mechanism formula, we know that we'll need to choose the noise with the B parameter being the sensitivity of these queries. And we've calculated that the sensitivity for all counting query for all linear queries is 1, and this divided by epsilon per okay, so we'll end up getting 1 over 0.005, and that's 200. Okay, so once we have that, and we can also work out the error bounds of answering all linear queries simultaneously with high accuracy. So again, it involves applying the utility bound that we established for Laplace mechanism, and this says that for every one of them, the error alpha is equal to b log. So error. So this is, I guess, yi minus qi transpose x. So we define this as alpha. So this is smaller than b 1 over delta theta, and this is 1 over epsilon per query log 1 over delta theta. This is k over epsilon total log 1 over delta theta, and by union bound over all I in, I guess, all queries in this query space, and then select delta theta to be 1 over delta over k. Then all these together says that max over all Q in this Laplace mechanism's output minus Q. This is smaller than I guess a space of Q over epsilon log of space of Q over delta with probability 1 minus at least 1 minus delta, right? So that's how we work out the error bound for many linear queries using like Laplace mechanism. So we can see that first of all, this is an unnormalized error, right? So if we want to calculate the normalized error, we should divide both sides by n, right? So we should observe that this error is on the order of this error. When I use big O tilde, it means that I'm ignoring logarithmic factor. And when we use the normal, so the error is on the order of Q over n epsilon. On the other hand, like if we got n samples and wanted to just calculate the mean, and we know that the n samples from some distribution, the statistical error is O tilde of 1 over square root of n. So there is a regime like for even this basic algorithm to outperform the statistical error, right? Which means that we can reveal like concrete information about the specific data set rather than about the population. But the catch is that when we do statistical error, then we can take union bound over all Q queries, and then the dependence on Q would be logarithmic. And when we apply Laplace mechanism this way, like this linear scaling in terms of the number of queries that we answer is really like it is really making it highly undesirable. Okay, like one more generic thing that we typically talk about is to translate this error bound of the form of Q log Q over delta over an epsilon into sample complexity. So this is error. This is a normalized error. And by sample complexity, we mean how large n needs to be before we get error, a normalized error alpha. So let's say that this is normalized error alpha. Then the sample complexity would be n needs to be on the order of Q log Q over delta over alpha epsilon. So this will be the sample complexity. Yeah, we need this many samples in order to achieve alpha error with probability 1 minus delta, right? So the true representation of either error bounds or sample complexity, they are equivalent to each other. Yes.
What is normalized error?
Oh, the normalized error means that yeah. So let me normalized error. Is an error between Q transpose X and Y. So this is a normalized error. A normalized error, you basically multiply 1 over n here. So this is a normalized error. And why is it normalized? It says that like when we normalize, it means that we care about averages. We care about proportions rather than the count, the total number of elements.
Shouldn't there be like a summation? So
yeah, the summation is in the Q transpose X. The Q transpose X, Q selects a subset of the individuals and then sum their secret bits up, right? So that's where the summation is. Okay, so we can also try applying randomized response to answer linear queries, and we'll see that it gives us a very different characteristics in terms of the error bound that we get. Okay, consider that this unbiased estimator that we derived just now, and then let's work out how we can make use of this to answer linear queries. So the naive algorithm is to say that let's just apply randomized response to output every secret bit for every individual, right? So by applying randomized response for by applying randomized response for n times, then we get we can output a bit vector that approximates the that approximates the ground truth bit vector. So x1 to x hat n, right? Which tries to approximate this x1 to xn. And I call this x, that's the original data set. I call this x hat. That's a approximate data set that's coming from randomized response. Okay, so the first thing that I want to argue is that since individual elements of this releasing say xi hat is epsilon differentially private, I argue that releasing the entire vector at x hat is also epsilon differentially private. Why is that? Yeah, so one student answers is because of post processing. Yeah, could you elaborate that a little bit?
So from my understanding, is that you can do whatever you want. So you can multiply by a vector and then do addition to that vector, so you have a single vector.
Yeah, but now we are concatenating like multiple access to the data set, right? So for x1, I need to access this data set by picking the first element and output it like approximately. For x2 hat, I also need to access the data set and then output x hat. Yeah, so it's not really post-processing because I'm looking at the data again. Right? Why is this okay? Think about what happens if you add or remove, or like in this case, think about what happens if you replace one individual.
So this when you write in the ratio form, that's only one of those. You take many it's like a vacuum.
Yeah, excellent. So epsilon dp is equivalent to say the log probability ratio of data set x, log probability ratio of data x prime, and the output is equal to say a particular value theta. Okay, and like since these independent randomized responses, they are independently drawn, and this probability distribution factorizes into a product for individual randomized responses. And since we're only adding or removing one person, since we're only replacing one person's bit, and all this probability will just cancel out except for that coordinate that's not canceling out. Therefore, like releasing the entire vector of output bits using randomized response also satisfies epsilon differential privacy without having to do any composition. Right. So more generally, this is known as a parallel composition. So when we apply a DP mechanism to two disjoint data sets where there are no overlapping among the individuals within these two disjoint data set, then the total privacy loss is a maximum of the privacy loss that got applied to the first one and the privacy loss that got applied to the second one. So in this case, it's just by induction, we're doing parallel composition over all individuals, and each individual having their own data set. All right, so now like a bit of detour on the privacy, and now having checked that the epsilon dp is fine when we are outputting the vector, now let's try constructing the answer the linear query by simply plugging in, right? So this is the most natural estimator. So since we want to estimate Q transpose X, so now let's just use Q transpose X hat as an estimator to the query. So this is equal to sum of Qi X hat of I from 1 to n, and we want to see like how close this is to Q transpose X. So this is the error that we're interested in. Okay, now let's first calculate the expected value of the error. notice that the only random variable here is x hat, right? Then and x hat is unbiased. We've established that when we in an earlier slide today. So this is equal to q transpose x minus q transpose x equals to 0. Oops. Now let's calculate the like the concentration of this q transpose x hat around its mean for a fixed q, right? So it's helpful to take a look at this expression. So notice that this is a summation of n independent random variables. Okay, so we'll introduce a hammer called Hofstad's inequality, which says that suppose you have x1 to xn that are independent, and suppose that these independent variables are bounded with probability 1 between ai and bi, then you can show that the deviation of its mean from its expected value being larger than some t goes to 0 doubly exponentially as t gets larger. So this is saying that when we sum like bounded random variables, it behaves more or less like a Gaussian, right? So let's try applying Hofstad's inequality to this problem so that we can show that with high probability q transpose x hat is close to its expected value, which is the correct thing, q transpose x. Okay, and the only thing that we need to do, we've already established that they are independent random variables because the randomized responses, they are independent. The only thing that we need to verify is really like to calculate what are these bi and ai parameters for each independent random variables. Okay, so the random variable is qi x hat I, and we know that qi is between 0 and 1. When qi is 0, this is 0 throughout. On the other hand, like when qi is 1, so this is a part where this random variable actually have some flexibility of moving around, right? So let's try figuring out what is the largest and smallest value for this to move around. So this is equal to just let's assume without loss of generality, assume qi is equal to 1, and then this will be 0.5 plus y minus 0.5 over 2p minus 1. And clearly this is smaller than the case when y is equal to 1 and larger than the case when y is equal to 0. So we'll work it out. This is equal to 0.5 plus 2p minus 1. 1 minus 0.5, we get 0.5, and this is smaller than 0.5 plus 2p minus 1. Y is equal to 0, so minus 0.5. Okay, so this is our bi, this is our ai, and all we care about is bi minus ai from this expression. When we apply Hofstad's inequality, so bi minus ai is equal to 2p minus 1, 0.5 minus minus 0.5, that's 1. And if we substitute the expression that p is equal to e to the power of epsilon over e to the power of epsilon plus 1, so this is how we calibrate the amount of noise to privacy requirement of epsilon. We can try substituting this into the expression and then get e to the power of epsilon plus 1, and I guess 2 e to the power minus e to the power epsilon minus 1, which gives us just e to the power of epsilon minus 1. Okay, so like with all these nonlinearities is somewhat hard to understand. So let's take two extremes. When epsilon goes to infinity, so for large epsilon, then this is just 1, right? And then when epsilon is small, this is roughly I guess 2 over this is 2 over epsilon. So this is roughly on the order of 1 over epsilon. Yeah, by small, I mean epsilon smaller than say 1. Okay, now let's substitute this bond of bi minus ai into Hofstein's inequality and then try deriving the error bound. Okay, so probability of 1 over n q transpose x hat minus q transpose x. So I'm just copying this over, take absolute value being larger than t is smaller than 2e to the power of minus n times something that's order 1 over epsilon, and on the numerator is 2n square t square. This n cancels with one of the exponent here, and what is the choice of choice of t that will make this probability delta, right? So let's try assigning this probability to delta, assigning this probability to delta and work it out. So effectively, log 2 over delta is equal to yeah, I'm I'm dividing both sides by 2 and then take log and then multiply -1 on both sides, right? So I get 2 and t square and some constant over epsilon, which says that I can choose t to be 1 over square root of n. Yeah, actually 2n and epsilon and c square root of log 2 over delta. Right. Yeah. So that's expression that I'm getting. So to say it differently, this says that with probability 1 minus delta, then the error of using this randomized response released x hat to privately publish the query gives us an error on the order of 1 over square root of n. Yeah. So error with probability 1 minus delta is order of 1 over square root of n square root of log 1 over delta and little epsilon here. Okay, I hope that's a clear application of Hofstein's inequality and how you would make use of it. So this is for answering a single linear query, and we can just make use of exactly the same data set, same synthetic data set that we released with x1 to xn hat to try to privately publish many linear queries with simply union bound, right? So using the same trick that we've learned before. So let me first copy this bound over. So for fixed q, q transpose x hat minus q transpose x smaller than some constant over square root of n square root of log 1 over delta tilde with probability 1 minus delta tilde. Then for all q in some query space at the same time, the max over q in q and q hat q transpose x hat minus q transpose x. By just enumerating over them and then apply union bound, this is smaller than c square root of n log square root of log cardinality of q delta tilde. I guess delta with probability 1 minus delta. So this requires us to choose delta tilde to be 1 delta over q cardinality. So this is the same argument that we used before by union bound over the k coordinates for the Laplace mechanism, and we're just doing the same thing for using the randomized response to answer many linear queries. Okay, so there's a question here, like why doesn't it depend polynomially in Q? Right, in Laplace mechanism, for every individual Q, we're adding some independent noise to that, right? But over here, we first privately publish the synthetic data set and then make use of the synthetic data set to construct as many answers as we want to all these queries. So for this reason, and due to the principle of closure to post-processing, it doesn't cause any additional privacy loss. Right. So if we stare at this and then compare the errors between Laplace mechanism and the randomized response, Laplace mechanism gives us an error of Q log Q over delta over epsilon, and randomized response gives us an so let's do normalized. Let's do normalized. So this divide by n. And on the other hand, the randomized response, instead of giving us 1 over n, it only gives us 1 over square root of n. On the other hand, the numerator is significantly better because it doesn't depend polynomially on the size of the Perry space. Okay, so when Q is very small, then the Laplace mechanism is better, and when Q is very large, then the randomized response is better. Okay, so back to the table that we had from the first lecture when we were constructing a specific attack which leads to blatant non-privacy. We've said that this reconstruction attack is really a low bar. That if we can blatantly reconstruct the data set up to the 90% of the query, 90% of its coordinates correctly, then no reasonable privacy preserving methods should like the lower bound would cover like all like privacy definitions, all meaningful privacy definition. Obviously, that includes differential privacy. So we can try to see like what is the what are the gaps here between like the provable impossibility results comparing to what we can now show that we can answer with differential privacy guarantees, which is arguably a much stronger privacy guarantee comparing to simply preventing reconstruction, blatant reconstruction. So let's like just first write down the two bounds that we have here from Laplace and the log Q over square root of n epsilon, and let's consider epsilon is a constant, so as to just get rid of the complexity, and for this question mark, for this question mark, can we do anything? If we just want a constant error and we want to answer order n linear queries, yeah, obviously we can do this because if we use randomized response, then the query space is only n, right? So we can even show that we can get errors 1 over square root of n. So randomized response applies here. How about the Laplace mechanism? Laplace mechanism also applies here because in this case Q is on the order of order n, so this evens out. It only gives us say a constant measure, Laplace mechanism. So this box checked. Can we go a little bit down to see whether we can get this box, the lower bound and upper bound to match? Yes, since we only want 1 over square root of n and the up to logarithmic factor, then randomized response here is optimal. And suppose we move to the right hand side when the number of queries is substantially smaller than n, then we can see that then we can see that in this case the Laplace mechanism is what can give you the errors that are substantially smaller than the statistical error, but only for only if if k is substantially smaller than the square root of n. So there's a small gap here. If all we want is a square root of n, then k can be proportional to square root of n. Then on the then Laplace mechanism achieves this error like up to a logarithmic factor in terms of log n. So apparently, if we want even smaller, even weaker results, then both Laplace mechanism and randomized response would apply to this box. So, how about here? Can we like answer up to on 2 to the power of n linear queries like while incurring only constant error? So let's try applying the bound of the randomized response here and then substitute the cardinality of Q to be 2 to the power of n. So we'll see that this becomes n, but then this divide by square root of n epsilon becomes a trivial result. So Laplace mechanism doesn't actually like obtain the lower bound in the case when k is 2 to the power of n, but it is optimal when k it is able to obtain the constant error when k is 2 to the power of square root of n. Yeah. So it looks like there are still like some gaps between the upper and lower bounds. And what we're gonna do next is to first take a break for 5 minutes, and then we will come back and to generalize this family of linear queries a little bit so that it applies to a broader family of problems rather than just keep thinking about this inner product of 2 bits vectors, in a somewhat trivial setting. So we'll come back and generalizing the linear queries and then talk about the algorithmic ideas that further improves over Laplace mechanisms and randomized responses. All right, I'll see you at 2:18. All right, as people start to walk back into the lecture theater, so let me slowly get the second half of the lecture started, because the least that I wanted to cover today is to finish the sparse vector technique, which still requires some effort. All right, so we'll start by generalizing the problem setting a little bit of this linear query. So before we talk about why it is called linear query, let's consider a family of so-called statistical queries that might be more familiar to you. So take the data table type of representation of the data set. So this is in n by d, and each phi I is in r to the d. And the statistical query is just the average of, say, certain transformation of individual data point. So we say that the Q of the data is a statistical query if it can be rewritten as some transformation f of q, where say for simplicity, so f of q output something that's between 0 and 1. Okay, so a few examples of this. Let's say that the average salary. So this is a statistical query. Let's say that the proportion of students who failed the class in terms of its evaluation, that's a statistical query. And in the context of machine learning, when the f of q is a evaluation of the individual gradients on a data point I, so gradient of the finite sum or empirical risk, right? So this is a statistical query because we can calculate the gradient of every data point and average them. Yeah, so the list goes on and on and on. So many things that we care about in practice are statistical query. So now I argue that in a different histogram representation that we talked about earlier, and this is simply linear in some function or some vector q in this space. Okay, so let me show you how that works. So for a statistical query, it can be decomposed into fq of phi of I. So I can further partition it into the sum of for like some elements of this data space. And then I can sum over f of q, phi of I, get an indicator that phi of I is equal to x. Okay, and this is equal to the 1 over n sum over all elements of the space, the number of x in the data set multiply with fq of x. Okay, which is 1 over n q transpose of the histogram representation of the data, and we just call this 1 over n q transpose x. Yeah, this x is not the same as this individual elements, but rather just the histogram representation of the data set. Okay, just by partitioning this, we can rewrite every statistical query into a linear query with some unspecified q, and this choice of q here is simply the f of q of x enumerate for all x in. So basically, yeah, that's a construction. All right, so I hope that's clear. And now we've like generalize the notion of a linear query into the more general sense that when we have a like general data set rather than just a bit vector, and luckily it is still linear, and we have this concise representation of the outcome of the linear query. And like obviously we can apply Laplace mechanism in exactly the same way, because all the statistical queries, and thanks to the fact that f of q is bounded, it satisfies the L1 sensitivity of 1, right? So we can still apply Laplace mechanism in the same way and obtain that q cardinality log q over delta over n epsilon error bound, like to answer all q in this query space. On the other hand, like maybe we can do a little bit better by applying Laplace mechanism in a slightly different way. So maybe we can just like in randomized response to privately release entire bit vector. So how about we use Laplace mechanism to release the entire data set in the histogram space? So what we can do is to release this. So these are the building blocks of all like statistical query, like effectively the ith coordinates, yeah, I guess the x coordinate of the histogram representation of the data, right? So this E of x is what I call the standard basis. That is a long vector that is 1 at x and everywhere 0, right? So this itself is a linear query and a statistical query. So notice that every coordinate satisfies that it is like smaller than 0 and 1. It basically selects out all the elements that are equal to x. Okay, so I can apply Laplace mechanism to mechanism to this E of x for all x in the query space, in the data space. And this gives us like a privately sanitized histogram representation of the data. So can someone tell me like what is the L1 sensitivity for releasing for releasing this for all x, for releasing this family of queries of a size as large as the size of the data space? What is L1 sensitivity? So I've asked this question repeatedly today from all those examples. Anyone? Yeah, but by releasing EX, I mean releasing this for all x in. You should think about adding or removing one data point inside this data set, and what's its effect in the histogram. Exactly, it's still 1, because this picks out one coordinates of this histogram, and adding or removing one individual can only affect one of the coordinates in the histogram. Therefore, releasing the whole thing satisfies the L1 sensitivity of 1. So adding Laplace noise to every coordinate of this histogram will give us a sanitized summary of the entire data set, and then later we can make use of it to output. Later, we can make use of it to output answers to other queries. Okay, so delta of f is equal to 1, and now that we got a hist data hat, and the like for any linear query, so we can use this as a surrogate. We can use this as an estimator. So clearly, since Laplace noise is unbiased, this is a 0 mean, and now also because each individual Also because Laplace noise is independent random variable, so even though we cannot apply Hopkins inequality because Laplace noise, they are not really bounded, but we can apply something called a exponential, like we can apply something called the concentration for sub-exponential random variables and obtain something that's very similar to what we get before. So instead of a doubly exponential tail, now we have a singly exponential tail, and it can be shown that this this way of outputting the query minus the Q hat the actual data histogram. Maybe let's add 1/n. This is like the first is the sum of the average mean of n IID random variable, and this is a true value. This is on the order of instead of 1/n, so this should be 1/1 over the cardinality of the data space, right? Wait, yeah, I'm sorry, I'm applying the normalization here. So the summation is summation over the data space, but since we're calculating the normalized error, so we're still adding this 1/n in front of it. Due to that, the equivalent representation of this as a statistical query. So for any statistical query, we can convert it into this linear query representation and have this 1/n in front. And since these are means of the IID random variable, and the scale of this mean of the size of the data space number of random variables. So what we can get is 1/√n square root of the size of the cardinality log 1/delta. Yeah. So this is a scale of the this is a scale of the error that we get. So it's not square root log 1/delta because this is exponential tail. Like this is sub-exponential tail rather than sub-Gaussian tail. And the reason why it is square root of the size of the cardinality of the data space, this is because we are adding a Laplace noise to every coordinate of the data space in the histogram. Okay, so this is by applying sub-exponential. Yeah, I didn't teach about this, so I'm gonna just informally discuss like this. Okay, so this could be useful in notice that this is now 1/n rather than 1/square root of n, and epsilon is also just here. This is 1/n rather than 1/square root of n. So this will be very useful when the space of when the data space is relatively small. So take the census application when any individual can be just a binary gender and say 7 or 11 different races, and they can be coming from like the a couple dozen states, and the product of them all is still much smaller than the population of the United States of America. Therefore, when you multiply 1/n to the square root of the cardinality of the data space, this could give you like a number that's substantially smaller than the sampling error. So that in particular improves over the randomized response version of the problem earlier. Okay, as a quick checkpoint, so we've seen that using Laplace mechanism to release a sequence of queries directly, it gives us this error. And when we do randomized response to release the data on a more restricted model of the linear release, then we get this error when n is a number of when n is a number of secret bits. And when we use the Laplace mechanism to release the histogram, like also known as contingency table, then we get this error per coordinate, and like the kind of error that we get. So this is unnormalized, and when we normalize, we have this additional 1/n here. Is proportional to square root of the cardinality of the space over epsilon. That leaves us with an open question of, because in some cases we have log of the total number of queries. In some cases we have log of we have logarithmic dependence on the cardinality on the size of the data space. The question is that whether we can get both at the same time, whether there is an algorithm that gives us exponential improvement by depending logarithmically or polylogarithmically in all these parameters, x cardinality and q cardinality, while achieving, say, constant error with a constant epsilon. Right? If so, then we can provably answer substantially more more linear queries. Okay, so before talking about such an algorithm, so let's consider a slightly different setting of improving the number of queries that we can answer in a somewhat more specialized setting. So let's consider the case when there's a large number of queries, but only a small number of them within this large number of queries that are interesting, that are meaningful for us to get the exact value. So I'll give two examples of why this could be useful. So the first is a anomaly detection in a time series of, say, count, and this count might be the number of products that are failing from a supply chain and then from a manufacturer plant. And if the number of if the number of faulty products increase substantially, then those are information that I should monitor and I should react right away, and we need to detect that. On the other hand, if the numbers are small, they are less interesting because there are nothing that I need to worry about. So having, say, 1 or 5 faulty with when I expect everything under 100 is reasonable, I don't need to do anything, then I probably don't need to know those exact numbers. In the second example, well, so maybe this will allow us to exploit additional information. So let's say that there is an oracle who can tell us about answers to these linear queries, and in a data independent way. Then if I can test whether the answer is correct or more or less correct comparing to the number that I would have gotten suppose I access my private data, and then like if I can make the decision like in terms of whether I want to listen to this oracle or whether I want to query the private data set for answers, then hopefully a big fraction of the answers that I need to query from the private data set will be saved. So I can save the privacy budget for the future. And to say it differently, I will be able to answer more linear queries accurately, like with the help of some oracle. And the example of such oracle is, say, a machine learning model that just takes a question and then try to come up with an answer. The answer may be right and maybe may have a large error. And if there's large error, then this answer will be very different from the answer that's coming from the private data set. The question is that, can we get away with paying only for those interesting queries, whereas like essentially paying nothing for those answers we decide that's not worthwhile getting the exact numbers? Okay, so that's the motivation of this setting, and it turns out that we can do this by like an extension of the Laplace mechanism, and the whole thing is called sparse vector technique, where the sparse vector is a sequence of queries, but only a small sparse subset of them is interesting, and the sparse vector techniques consists of multiple applications of this so-called above threshold mechanism. So let me explain how above threshold mechanism works. So the above threshold mechanism takes a data set, and then there's an online sequence of queries, F1 to Fn, like possibly infinite sequence of queries, but each one of them has a sensitivity of 1. Let's say that the user gives you a particular threshold T to decide whether the answer to these queries will be interesting or not. Anything that are larger than this threshold is interesting. I'd want to label them, and anything that is smaller than this threshold, I find them to be not so interesting. Okay, and the output is a sequence of the sequence of responses of a sequence of bit vectors, and when we have this top sign, so this is top and this is perp, like both of these are in LaTeX notation. When it is perp, then it basically is, so we don't need to do anything, and let's continue. And when we receive an output of top, then we stop. It means that we've discovered something that needs to be dealt with, and then this algorithm stops. Okay, so this is a like iterative algorithm that keeps looking at the output to the query, and will add noise to the threshold. We'll add noise to the threshold. We'll also add noise to the query, and then determine whether this query is larger or smaller than this noisy version of the threshold. We perturb the threshold first, and then we go over a sequence of query until we find something that is interesting according to this decision rule. So the intuition of why we need to perturb the threshold is really that even if we're not outputting these numbers exactly, if the threshold is not perturbed, and then the output bit vector itself contains information about the individual queries. So that's a high level intuition, but like since we'll be clear in the proof of why this noise that's added to the threshold plays a central role in understanding how this algorithm works. And one remark that I want to make about this algorithm is that it has this remarkable property that it can potentially be used to answer an infinite sequence of queries with bits without seeming to be paying anything that depends on the length of the sequence. Okay. So now, how does the sparse vector work? Sparse vector basically is a composition of C above threshold algorithm of like composition of this for C time. So what we can basically do is to first split the privacy budget into C equal parts and run above threshold for each one of them with a parameter epsilon over C. And the end goal of the sparse vector mechanism is to discover a maximum number of C elements within a sparse vector. Yeah, for however long this sparse vector is. And we will stop when either the stream of queries is done, when we finish all the items, or the all C discoveries are already made. Okay, so that's sparse vector mechanism. You can already see that if we show that the above threshold mechanism epsilon over C dp, then that implies that by composition, the sparse vector mechanism is epsilon dp. Okay, so SVT has many variants in the literature. It's notoriously tricky and difficult to analyze. And here are like a summary of 6 different versions of SVT according to this paper. And it turns out that this paper is like this version is wrong. This person is also wrong. This person's wrong. This version is also wrong. So many of them do not satisfy epsilon dp with epsilon smaller than positive infinity, and then some are off by a factor that depends on the number of rounds. Some got those parameters right. Only the first 2 versions are correct. So we're going to be covering the second version, which notably refreshes refreshes the threshold after every iteration, whereas this version, it doesn't refresh the threshold. It analyzes sparse vector technique altogether rather than consider it as a composition of C different rounds of above threshold. So this is the version that we'll consider. And in fact, we're going to be analyzing a slight generalization of this above threshold mechanism. So instead of just considering Laplace noise, we'll be analyzing any noise adding mechanisms. Say the threshold noise is uses the mechanism M1, which add like arbitrary distribution, but the arbitrary distribution at noise Z that needs to satisfy that M1 is epsilon over 2 dp for all queries with sensitivity 2. And then instead of analyzing just Laplace mechanism, we'll say that the M2 is a mechanism that we use, a noise adding mechanism for adding noise to the queries themselves. And M2 is epsilon over 2 dp for all queries. Sorry, this is sensitivity 1. Queries with a sensitivity with delta equals to 2. Okay, so it's a slight generalization of the above threshold. Well, so we'll denote the random variables of the noise that got added to the threshold by Z. We'll denote the random variables that are added to the threshold in every iteration by this nu. So nu1 to nu k. Okay, so the corresponding queries, so here it is denoted by f of I. So let's just revise the notation a little bit and denoting them by q1 to qk. So these are the sequence of queries that are selected by the arbitrary adversary that can depend on things in the past. Okay, so before we talk about the idea of the proof, like we probably don't have time to go over the full proof today, but let me tell you about the ideas. And we need to talk about these elements of the proofs. To begin, I'll first make the following remark. So if we stare at how this algorithm works, it only stops when the output is top. If the output is perp, then we'll keep going. Right? So in other words, the output space of this algorithm is a infinite set, but the set is the output is always of this form. Okay, so this means that the output can be completely described by a random integer k. Right? So, or in other words, stopping time. And then the second remark that I'm going to make is without loss of generality, we can assume t to be equal to 0. So t is a threshold that we set. We can simplify the problem a little bit by always choosing t to be this t to be 0. Why is that the case? Because we can always redefine these queries by defining these queries to be fi minus t, which itself is also like a sensitivity 1 query, right? So this helps us to simplify the notation a little bit. And lastly, like I argue that the probability for the algorithm to output k can be described by this like seemingly complicated integral, which so we'll use this p of rho to denote the density function of the noise that we add to the threshold, and we'll use this p to denote the noise that are added to individual queries. Okay, so these are the same, and these are the p rho or noise added to the density of the noise that are added to the threshold itself. So what this equation says is really by applying law of total expectation, law of total probability by just writing down like what's gonna happen to give us this output. So first of all, let's condition on the realized value of z. And once z is fixed, then in order to get this output, it means that the value of this nu I needs to be between -infinity to here. So this is saying that now this is Z. Notice that the threshold is 0. So this is a threshold, and the decision rule of this algorithm is to output top if the query plus noise is larger than the noisy threshold. So now the noisy threshold is here. Then this is saying that we're not stopping because this random variable ended up within this range. Right, therefore we're integrating from -infinity all the way to so this is a qi plus nu I is in this range. Therefore this nu I is in the range of Z minus needs to be smaller than Z minus qi. So this is Z minus qi. Right. That's why we're just calculating the probability of qi plus nu I is smaller than Z. Lastly, like we are only stopping at k because for the last element we are actually stopping, right? So this is saying this is the probability of q k plus 1 plus nu k plus 1 is larger than Z, right? And we're just writing it in the integral form here. Okay, so if all that is clear, this is just like a rewriting of that. We first, by applying law of total probability by condition on the realized value of the threshold noise, and then we decompose it into the product of this independent event, so that the output is perp to the power of k multiplied with top. This is output. And then we basically like rewrite everything from the previous slide. And now like the trick is to do the change of variable by defining this u such that u is equal to Z plus this sensitivity delta, and in our case delta is just 1, and then we can substitute this. But we can substitute Z is equal to U minus delta into the above equation, right? So Z got replaced with that, Z got replaced with that, and Z got replaced with that. And like everything's still equal. And once we have that, like the idea is that we now multiply and divide by P row of U, right? So we can always do that because this is non-negative. Now like we can just take U to be equal to Z by calling this Z again, right? Now everything decomposes into 3 terms. The first term is something that we can actually bound using the definition of differential privacy. So notice that we assume that this Z noise satisfy that it is half epsilon differentially private for all queries that are that has sensitivity smaller than delta, right? So therefore this is smaller than e to the power of half epsilon. For the middle one, so this is the most interesting part. Let's say that this is Z minus QID. Okay, and this is the probability that this nu I can be getting in here. Like so where like minus also minus delta. So where could and this is delta and this is Z minus QID. So where could where suppose we replace D with D prime, which is a neighboring data set, where could Zi minus QID prime possibly be? Since QI and QID and QID prime, they differ at most by delta. So I argue that it can it needs to appear yeah, it needs to appear within this window, plus and minus delta, right? So no matter where this is, it needs to be somewhere within this window. If it is within this window, therefore, when we are replacing the place that we're integrating to z minus qi d prime, then it gives me a bigger probability. Right? Because the set is larger, therefore we can bound the middle term with pi the product of I smaller than k minus infinity to z minus qi d d prime, when d prime is a neighboring data set and p nu I and d nu I. Right, so now we've aligned the first term and the second term with the kind of probability of having. So the idea is that we want to construct md prime is equal to k on the right hand side, right? So far we've done the first thing and the second thing, and it remains to bound the last term, right? So yeah, I guess it's 254 here, but yeah, so. Let me see if I have time to do this. So let me do a very quick one. D minus delta, oops, minus qk plus 1 d to positive infinity, and p of k plus 1 nu k plus 1 d nu k plus 1, right? So this is equal to the probability of nu k larger than z minus delta minus qk plus 1 d, right? And the key idea here is that we want to define some fictitious query called q tilde, where q tilde of d is equal to qk plus 1 d plus delta. So I can replace this with q tilde of d. Now this is equal to p of q tilde of d plus nu k plus 1 larger than z, larger than the threshold z. And now, like, and notice that q tilde of d, since qk plus 1d differs by qk plus 1d prime by at most delta, and q tilde minus qk plus 1d prime is smaller than at most 2 delta, right? By the definition here, and also by the d and d prime are neighboring data sets, and this is smaller than 2 times delta. And now by the condition we have about the query noise that needs to be epsilon half epsilon dp for all neighboring, for all queries satisfied that its sensitivity is smaller than 2 delta, then we can bound this by 2 to the power of half epsilon p of q k plus 1 d prime plus nu k plus 1 larger than z. We can bound this. And then by substituting this back to the equation over here and combining the leading factor of e to the power of epsilon, and then checking that the expression is exactly the same as this, but with d replaced by d prime, then we've checked the definition of differential privacy, and this establishes that the above threshold algorithm is epsilon dp. The generalized above threshold algorithm is epsilon dp. Yeah, so the argument is somewhat delicate. I encourage you to read the slides and then revisit the video of the lecture carefully. But that's what I'm gonna. That's where I'm gonna stop today. And in the next lecture, I'm gonna talk about how we can make use of the sparse vector to construct and the exponential improvement in answering linear queries. All right, thank you for coming.